Okay, so let's have an example here, and in this example we are going to deal with the function that we have already explained in the previous video. This function f of x, it equals to x when x is between 0 and L over 2, and it equals to L minus x for x between L over 2 to L. So we have these intervals of the functions. Now with f given by the equation 16.4 and with L equal to pi, so we are going to use L here equal to pi, so it is limited interval. The first thing is we want to calculate the coefficients, right? The coefficients, or the coefficient that we are going to deal with, which is Cn, right? In the previous video I mentioned about the coefficient that we need to calculate. Let's go back here. So the function, or the wave function, is going to be described by, first of all, this coefficient, which is Cn, and then sine something related to x, and then cosine something related to y, right? So the first step is to obtain Cn. Okay. Now this Cn, as we said, 2 over L, from 0 to L, it is the integration from 0 to L of the function itself with the independent parameter z, sine n pi z over L dz, right? And then the Cn, we are going to just substitute here and make the integration. It's going to be an easy one. So from 0 to pi, so we say that it's 2 over L or pi, from 0 to L or 0 to pi, the function f of z sine n z, okay, dz, because n pi z over L. Okay, so we have L equal pi, so this would cancel the pi here, and we are ending up with nz dz. And then we are having two intervals, right? Two intervals. So one with x, another one with L minus x. So from 0 to L over 2, or pi over 2, because we have here, this is pi over 2, right? And the other is going to be the second interval, which is from exactly L over 2 to L, which is the function in this part is going to be f of x equal to L minus x, which is pi minus x here, or sorry, pi minus z in this case. And here in the first interval, the f of x equal to x, which means z. And then we are going to multiply by this term, which is the sine term, sine nz. That's it. So it is going to be sine nz here, and then sine nz here. That's it. And then we're going to make this integration. Let's clean up here everything. We're going to make integration. We are going to end up with, this is the coefficient value. So it's the coefficient, as you can see here, it is sine n pi over L over pi n squared, like a constant. It's like a coefficient that is going to be used. Okay, so the solution of this problem, again, what is the meaning of the solution? Means that the wave equation that we are going to use, it is going to be y of x and t of our equation, or of this wave, going to be described by putting coefficient here, which is this coefficient, for sine n pi over 2 over pi n squared, times sine nx cosine nct, right? So sine nx, this is n, the number of terms that we're going to take. We can decide whatever we want. And n, c, this c, we said it is a constant, like depending on the like density or rho of the robe itself. It's a constant, it's going to be given. And then here t, a different t. So we can say, if we have this constant, for example, c equal 2, we can get t, or the shape or the position of the wave at different t's, right? t1, t2, t3, and so on and so forth. Okay, and this is what we are going to see for this shape of the function. As you can see here, this is the shape of the function here. Here, this is at t equal 0.3, the wave was taking this shape. Okay. And then at 0.6, it will take this shape. And then at 0.9, this one. And then t equal to 1.2, it is going to revert here. Okay, so this is the wave, as we said, because we started from something like this, and then we're going to end up with like going from one case to another. So this is how the wave function is describing the position of any particle on the wave with respect to x and the time as well. Okay, so let's go back here to this function, or this wave function that we have. Again, we are using like several terms. There is a coefficient, like a constant here, for example, times one term relating x, another term relating t, and there is a constant here. Okay, so this is this is what I have said to you. So we can, like any function that is any function that is having exactly zero initial velocity, we can describe it easily with these three terms. Okay, cn here, and sine something with x, and cosine something with t. Okay. Okay, so this is the this example. Let's go to another example and see how we can apply the same concept on another function. We will solve for y equal y of x and t on the interval from 0 to pi, which is L here, okay, with zero initial velocity. And the initial position, this is the initial position, as we said, this is the initial position, as if we are like giving the initial position of the wave, giving it something like this, for example. How we can do this? By giving the function this value, x cosine 5x over 2. And remember that even that x, it's like seems to be variable. That's right, because we have x here. It is always going to be changed. So at every x there is a shape for the wave. Okay, so for example, at x equal 1, for example, what is the function? It is going to be put here 1, and then you are going to obtain the position of the rope at x equal to 1, and then x equal to 2, and x equal to 3, and so on. So this is what we call it initial position. So initial position, it is not like it is constant in terms of x variable, because we have x variable along x, right? Okay, so this is like the initial condition here. The coefficients are, we are going to obtain the coefficient first, Cn. It is going to be 2 over pi, okay, 2 over pi, the integration from 0 to pi, which is L, f of x times, which is going to be our function here, which is f of z, which is f of x here. We are going to use f of z, exactly. So it is going to be f of z. So z cosine 5z over 2, and then we are multiplying sine n z, because it is sine n pi z over L. L cancels with the pi, as we said before. So now we have Cn. It is like limited integration. We can solve it easily. You're going to find it something like this, 8 over pi, and you can find n here, and you can find n also in the denominator, and then this is the coefficient. It's a coefficient constant, and then we can say that the solution is going to be, which is the wave function at any time. Remember, what is the difference between this f of x equal x cosine 5x over 2? It's a fixed, it's initial at certain point at 0, t equal to 0, for example. But after that, we want to describe it at different t's, right? So we are going to put our Cn here as the coefficient, and then we're going to multiply sine times sine nx. This is the variable x here, cosine nct. This is the variable t here. C is going to be constant. It should be always given to you, because it depends on the condition of the rope itself, like the density and so on. The following figure shows wave profiles for C equal to 1 and at times 0.1, 0.3, 0.6, 0.9 moving downward over these times. Let's have a look on it. Exactly how this is. So you can imagine here, this is, for example, at t equal to 0.1. Can you see this? I'm going to make it like here, 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 here. This is 0.1. Can you imagine where is 0, for example? At t equals 0, I think that it is going to be something like this, for example. I'm not sure, but anyway, this is maybe something like this is how we started with. This is the initial condition that we started with. And then this is 0.1. Let's clean here. This is 0.1. Then this is 0.3. This is 0.6. And this is 0.9. So it is going like first one, then second one. I hope that I'm following the right path. And then the third one, this one. And then the fourth one, something like this. It is like flipping here. Okay, so this is the wave profiles of the equation. This is how this equation is defining the wave function. It is graphically is going to be defined as you can see it here. Okay, it's graphically is going to be as you can see it here. Okay. This is, again, I want you to remember well, because we have like different variables. Remember that this part, it's the coefficient, constant. This part is the contribution of x along x, how the wave is going to be along x. And this part is the t, what is the, like at time t, what this point, where this point is going to be here, 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 where exactly. So it is going to be something like this, something like this, something like this. So this is like t. And then another one is providing x, how the profile of the wave is going to be in x direction. Okay, so this is the sign in x. Okay, okay. That's it for the case of zero initial velocity. Okay, and I hope that next time we can like go through the understanding of another initial condition, which is zero initial displacement. Okay, okay. Thank you, and see you in the next video.